Next up, we have Derek Giardino with NOAA. So Derek is the senior hydrologist who is currently a leader in flood inundation map in the flood inundation mapping team within the Geospatial Intelligence Division at the Office of Water Prediction for the National Weather Service. Previously, Derek worked for 15 years at the West Gulf River Forecast Center, where he led efforts in forecasting and issuing forecasts across Texas, New Mexico, and Colorado for events like the major flooding in Texas in 2015 and Hurricane Harvey. With a master's degree in civil engineering water resources from the University of Central Florida, he also has a bachelor's degree in meteorology from Northern Illinois University. Derek actively engages with the scientific community, presenting flood mapping innovation at organizational conferences for the American Meteorological Society, the Cooperative Institute for Research to Operations in Hydrology, and the National Weather Association. Derek, I'll pass it off to you.
Thanks, and thanks to ChatGPT for that introduction that I was able to find. I'm here. I thought it was interesting to hear. Yeah, we have like local level research, and obviously, and then we went to the state level. Well, I wanted to present something from the federal level, and I'm going to talk. We can go to the next slide. Today, I'm going to talk about a little bit on our agenda is the National Water Model, which is available everywhere, but my bread and butter, the flood inundation mapping. How it may help forecast utility for transportation, and not just in one state or everywhere. We're trying to do this for the entire CONUS, for every stream, reach, and river, from actually CONUS and OCONUS. And I'm going to talk a little bit about Hurricane Helene, which seems to be a hot topic, so I didn't want to be left out. And then at the end, I'll leave you with some slides on data sources where you can grab and utilize the data yourself. Next slide. I just wanted to point out where we sit with our federal partners, as well as where we sit with other research initiatives and states, but we really all work together in a cohesive unit, and we are the forecast branch. We try to get things out ahead. You see a lot of people work with the observed or utilize our forecast to take into their own tools to generate something that's value to them. So it isn't just us, even with forecasting. We use release information from the Corps of Engineers for water management. The USGS is a really close partner. And then FEMA takes all the data that we can possibly give them and try to find some kind of response, and then post-event some mitigation techniques. We don't do this alone. We work with academia. In fact, we have an entire university consortium that works with us called Cairo, basically our research arm that involves, I think, 30 to 40 universities that are getting research grants to help us advance our tech. And I can be honest with you, everything I'm showing you today came out of research from universities, which is, I think, the way it's supposed to be. And then lastly, we could do all of this, but if it doesn't get down to the emergency managers, the stakeholders, the people pulling people out of floods and closing roads and keeping them safe, it's all for naught. So this is all really just to get to the emergency managers and the people that, like you guys on this call, to get people from driving through flooded roadways, which is obviously the #1 cause of death. Next slide. We'll talk first a little bit about the National Water Model. So we can just move to the next slide, and I will talk about what we're doing. So we talked a lot about river forecast centers in North Carolina, which are vital. Those are the key gauge locations. There's about 3,600 forecast points across the United States. That equates to about one forecast point for about every 1,000 river miles, since there's 3.4 million river miles in the United States. The National Water Model tries to fill that gap. We got about 2.7 of the 3.4 million river miles modeled, forecasted, and gives you hydrographs for reaches which mostly value under a mile each. So you get a lot more data that we could utilize, but as we've seen, this is not QC'd. These aren't always at the most critical points, but it does give you data, a little bit of data everywhere. And it's been evolving, and it's going to be in its third version here. Actually, it's already in its third version. We're going to a 3.1 here shortly. And its accuracy has only increased. And to me, as just your general hydrologist who used to work in a river forecast center, the areas above your first forecast point, it provides all this data of the water that could be coming from the headwaters. It's invaluable. I really appreciate getting a little more advanced notice before it just pops up at a gauge. Next slide. So the value of it is all perspectives. And that's really what we're trying to do federally, is be able to provide value with the limited amount of products, but gives you value both at the national, regional, neighborhood, and stream scale, like stream gauge scale. So the water model does that. You're able to just get a snapshot of what's going on across the nation. You can zoom in and get a little more information about the region, which is really helpful in tropical situations. FIM and some of its work is available at the neighborhood level. And then when you get a stream scale, there is a hydrograph available at each water model reach. So you can really drill down and get a forecast just about anywhere. Next slide. And giving an example of here in North Carolina, the red points are the points where we have a river gauge, and the blue lines is where you can get a national water model forecast. So you can see the evolution that we're trying to fill in and the data gap we're trying to close by having this automated national water model. Next slide. And I just want to give you kind of a trajectory of where we are. We started this in 2016 to 2018, again, as a research initiative that came from University of Texas and several other universities that contributed, brought it to the National Water Center, and we began making version 1. We've made upgrades and improvements to accuracy, including expansion to Hawaii and Puerto Rico. And then we've had our 5th upgrade, or version 3.0 in 2023. We're beginning to get into that total water level realm. We're not trying to step on the Hurricane Center's toes at all. They are still the storm surge masters, and we appreciate all they do. What happens when the water is starting to recede? How much of that fresh water is impeding over it? How much is it combining? That's what we're trying to model. We're working on it internally. First versions are always just like the first versions. We're learning a lot. We hope with version 3.1 to have a much better understanding of the total water level. We also expanded to Alaska. And the next version is heterogeneous modeling, not just using one national water model, but being able to swap in HECRAS, 2D, Mike 2D, other models that might be able to help us stitch together the best modeling across the nation. That's version 4 coming in 2026, 2027. And we can skip ahead, next slide. We'll start talking about the FIM here. So we can go to the next slide. This is my bread and butter. This is my development division. And basically, this is a fancy GIF that if you cared to know the science behind it, the simplest way to explain it is that for a grid across the entire nation, the flow lines represent the bottom, and we just drain everything in a grid towards that bottom. And then we move it downstream. That's the hand method. It is a basic method, but it is efficient to run for the entire nation. So we are running right now, as we speak, about 1 terabyte of data every day, creating flood maps for the entire nation. Next slide. So our kind of development plan and how it came through, again, Water Center Summer Institute, which is where we bring researchers in. They were the ones that basically took the water model and decided how can we design a flood map around it. So this came from researchers. This came from many people on our team right now that are on the team, came in as people who were students that came out to the summer and said, can we do this? Then we did our first, what's called agency priority goal, which in 2019, they came basically to me at West Gulf and said, rerun Harvey and rerun the devastating flood in Wimberley, Texas, and see if flood maps would have helped. And we got a lot of great feedback, a lot of great improvements to make. And that's what led to the second priority goal, which we did up in the Atlantic coast. And now we made it operational about a year and a half ago for 10% of the nation, about half a year ago for 30% of the nation. And we are moving to 60% in this September 2nd, and we'll go to 100% by 2026. You can go to the next slide. I think it will be a map of where we're releasing and how we're releasing. So you can see Texas and where we did the first 2 tabletops. Oh, back one. Yep. You can see in the green, the Forester green didn't make this. But forest green, you can see that we did first, and we keep flying around. The 30% is what we filled in. And if you'll key in on North Carolina, we literally put this out the day before Helene made landfall. I rushed it out to try and get something. Mind you, the area in yellow was not released publicly, so it was not available in Helene. We have all the data from Helene. We've looked at it and tore through it, and we sent a lot of it out during Helene to internal partners like Red Cross and FEMA. But it was a disappointment to me personally to not have that available, because in the mountainous regions is actually where we excel. It works well with high terrain. In the flat terrains of Houston and all of Florida is where we struggle and are working on some other methods. And that's why the Florida is the last, the 100%. Try to give us some more time to develop a solution for flatter terrain. All right, we can move forward a couple slides, as I want to talk a little bit about how this is going to apply to transportation, which I'm sure is of interest to everyone. Yeah, next slide. Thanks. Back one. We're giving away the solutions there, but the first thing we want to do is we took this from North Carolina, which was great to see it here, is about bridges. We wanted to make our own bridge alert network, not just for one state, but expand it to CONUS. The first method we did is we just used OpenStreetMaps. On every bridge we tagged, we found, we basically took the embankment elevation, connected it, and said, that's the bridge deck. And when we did that, we were able to basically have the simulated bridge deck. And when the water elevation passed it in a forecast mode, we'd be able to forecast that this bridge could be threatened. That is available internally to our weather service employees as of probably the next 2 hours. Like, we're just getting this done, which would be a great tool for our forecasters to be able to message bridge threats and potential impacts to transportation. We are adding LiDAR healing to that situation. That will be available in a few weeks. The LiDAR basically improved the embankment height. So we're not just using the embankments to connect the bridge, we're actually using the actual bridge heights. We have OSM embankments for about 700,000. We have the LiDAR, where we actually got the LiDAR bridge deck classified for about 300,000. So about half will have LiDAR bridge decks available. We're going to try to use machine learning AI guided to correct the ones that do not have LiDAR. That's in a future build. And then the next frontier, as we like to ride on North Carolina's coattails, is trying to figure out road elevation impacts for the nation. We're hoping to have that in early 2026. Next slide. Just some examples of how we do one. The top left is the OpenStreetMaps method. You can kind of see the digital elevation model that kind of ended over the river there on the left. We connected it virtually, and then so we did that in the mapping phase so that the map doesn't show the flood going over top the bridge. You can see in the animation, the left one is what we had before we had that developed, and some of those bridges were overtopped immediately or always. And on the right, you can see that as the flood grows in each level, each stage level, eventually they will become inundated and overtopped, better identifying. Mind you, we don't have the road network in there yet, still burnt base level, so that's the next frontier. Next slide. And just an image of what the LiDAR looks like and when you can and cannot use it. The one on the right, we could use. The one on the left, you can see it's just a bunch of unclassified. And to try and classify that for about 300,000 bridges that had a whole bunch of unclassified became cumbersome. And that's where we'll try to use machine learning to link the two. Next slide. So let's dive into a little bit about Hurricane Helene. And this is a great image because this is a forecast. This is a forecast of the potential flooding that could be happening across North Carolina during Helene. This was available because the water model is publicly available, just not the flood mapping to accompany it. And this forecast shows much better than just the river gauge points of what the flooding footprint could look like, and all the rivers, streams, and creeks. And you can see South Carolina, North Carolina, all being impacted by Helene. I wanted to just show this because I love the river forecast centers. I come from the river forecast centers, and I know there is a lot more flooding going on than at those certain gauges. And I've written a lot of those impact statements at river gauges that extend several miles away, which is making a whole bunch of assumptions. And I do think the water model fills in the gap and completes the message for you when you're trying to find more information for an area that doesn't have a gauge. Next slide. In Hurricane Helene in Tennessee, I'm sorry, I'm leaving North Carolina, but in Tennessee, this shows you how you can put all three of them together. The water model On the left, that was the forecast out there on 9/25. We were able to, the FIM that was generated based off that water model was available and shows NOCoE Hospital going underwater in Tennessee. We alerted the hospital, who, again, the job of the Weather Service is to alert of when a high hazard is there. We cannot recommend evacuations. That is the locals only. We did not recommend, we told them they were threatened. We recommended that the EM issue an evacuation, but the EM said it's still to the hospital. They did not evacuate. And so they were helicoptered off the roof. And the reason why they were helicoptered off is because the EM knew they were threatened, knew there was going to be issue, and had stuff staged and resourced ready to get them off the roof if something happened. So the hospital was evacuated and there was no casualties, no impacts to human life, other than obviously the distress of seeing the water come up overnight. But that's, you can see how you get the water model tells you where to look. The FIM tells you how bad it could be. And then the messaging has to be completed to get everybody into safety. Next slide. Another example of putting all three on one map. This is an RFC forecast point downtown Asheville, just up the stream. And you can see this was the message they put out about the life-threatening flooding. I still don't, you can't get rid of the hydrograph. The FIM is great. It tells you where the flooding is, how extend wide, what structures may be impacted, but I don't get the message of when, how high is it going to go, where are we in the forecast realm? If this is the maximum, when is it going to happen? Where is it at now? The hydrograph still holds a lot of value, and I'm glad we're still including it, and the River Forecast Center still provide a lot of value to everyone. We can go to the next slide. And this will kind of show the result of that exact map being shown on the left. And there's the visual from the person taking the image for Forbes. What you can notice is in the background, we showed that the bridge was not going to be impacted. And at the time of this image, you can see the bridge is still open in the background. And that's what we hope to do with bridges, because it's not just what is closed, but what can be left open for resource transportation. You know, can we get a boat cruise over to the other side of the river? If we can't, we got to stage them early. We got to put them out there before. And that's what we're trying to do with the forecast mode. All right, we can go to the next slide. I just want to put this out there, and you can go to the next one. These are just data sources for you and links. You can go to our NWS page, water.noaa.gov, and you can see where we have FIM available. You can see our National GIS viewer to see the water model as well. I also have Esri REST services. If you want to bring them into your own accounts, you can do that. We're just trying to get you data the way you want it, and you take it wherever you need to go with it. And then the next slide shows you another data source. That's our operations page, has links to flyers, updates, more information, but you can go to the next slide as well. That's my info in case you need more information that you can't find, or you